Hello! In a previous video, I talked about how data was written to a floppy disk. If you haven't checked that video out yet, then I suggest you do before continuing, because in this video we're going to build upon that information and talk about the various different copy protection techniques that we used.
Did I hear you right? Did I hear you saying that you're gonna make a copy of a game without paying? Come on, guys! I thought you knew better, don't copy that floppy!
I'm sure some of you will remember that 90s video, Don't Copy That Floppy, and all the coverage around the subject. There was a big international campaign to prevent software piracy, and so developers and publishers found ingenious ways to make this more difficult.
Protector for you and the posse, that's the artists, writers, designers, and programmers that worked up the...
We're not going to look at copy protection that involves code sheets or looking at particular words in a manual. In this video, we're going to look at physically how they prevented you copying a disk. First, we need to understand a few things. If you remember from the last video, the drive and various components were able to manage an unstable clock interval from the drive. But when the data is written back again, it's written back at a precise clock interval. Most of the computers of the era could not vary this interval. It was always 2 microseconds for double density disks and 4 microseconds for high density. Aside from this reading and writing, a standard disk is usually broken up into sectors. Typically, each sector starts with a sync word, followed by the sector header. The header usually includes such information as the sector number, header, and data checksums. An operating system would look for these sectors and load the specific sectors required, sometimes called the root block, to read the contents of the disk and therefore show the file system. The first method we'll look at, although very basic, is to simply encode the disk in a format that was non-standard to the operating system. The operating system's disk copy program was quite often a sector-by-sector copy, and if it couldn't identify the sectors or the format of the disk, it was unable to copy it correctly. By having the disk in a non-standard format, for example by changing the sync word or not including any of the expected file system information, would prevent these programs from copying the disk. Another method used was to deliberately encode a sector with an invalid checksum. The operating system would correct this checksum when it copied the data back to the disk. The software or game would then read the disk and see if this checksum was correct or not. Another method used was to hide data between sectors. The start of the sector is typically marked using the sync word a number of times. Immediately after this would be the sector header and the data segment being of a known size. If extra data was added to the end of this, for example between two sectors, then any software that performed a sector by sector copy wouldn't see this data and would get missed out on the copied disk. So those are some of the more basic copy protection methods. It's not too hard to bypass these, and a simple bit-by-bit copy of these will easily work. So now let's move on to the more interesting ones. The first one I'm going to look at, whilst interesting, was rarely used. It meant you had to leave the disk write enabled. The disk had been produced with a small area within a sector that had some kind of defect or damage. This bad sector would prevent writing to a small section, but the area around it would write perfectly. The software could attempt to write to it and then read it back. If the data was partially read back correctly, the software knew this was the original disk. Another technique used, which worked fairly well on platforms such as the Amiga, was to align data at or within some time of the index pulse. The Amiga didn't typically index align its data when written. It wasn't important. And so making a copy of these tracks would have them all start at random positions. The software could easily detect this. This is, however, fairly easy to defeat. Some games would even read the data on the disk until it encountered a specific location, and then immediately switch to either the other side or move the head to another track. The software could then read the data at that location, and if it wasn't what it expected, then it knew this was a copy. Copying this would be quite tricky as perfect alignment of data between tracks was important. For the purposes of the next methods, I have created a simulator to help visualise what's going on. This shows an example of data coming in from a disk. This is happening a lot faster than from a real disk. Each time the image updates, the simulator is behaving like an entire rotation of a disk track was read. The white dots represent the time since the previous dot, and as this is a double density drive, they roughly fit into the 4, 6 and 8 microsecond sections. You'll notice they move around a little, and the whole pattern waves up and down. This is to be expected as the drive motor had slight variations as it spins the disk. Also, because of the auto gain, there's further jitter in the positions. Lastly, of course, there's the PLL. The yellow line represents the current clock used by the PLL, and as you can see it waves up and down as it follows the pattern of the data. At the bottom you can see some kind of bar graph. This graph represents how the data would have been interpreted from the disk. The red bar represents a 01, the green a 001, and the blue a 0001 MFM encoded. This is a simulation of a perfectly normal disk. This, however, isn't. This is a simulation of a disk using long tracks. Long tracks will read perfectly well as the PLL adjusts to the slightly higher clock rate. The flux transitions are lower on the screen, meaning they're happening slightly faster than usual. This also means the data is loaded slightly quicker. As a result, it's actually possible to fit slightly more data onto the disk than would be possible normally. This is a simple form of copy protection. When attempting to write this data back to the disk, the computer assumes the normal 4, 6 and 8 microsecond timings. Most hardware of the era would be unable to change these, and as a result, the data is actually too big to fit on the track, and you would end up overwriting the start of the track with the end. Ironically, when games like this were cracked, they often came on more disks than the original game. Here's another clever technique. Remember in the previous video I said if there wasn't any flux transitions for a while, the drive would start to output random data? Well, this is a method used in copy protection too. Typically, a single sector or sometimes an entire track is left unformatted. When the disk is copied, a snapshot of this data is written to the disk. This snapshot won't change randomly like before, and the software will keep rereading the data on these tracks looking for changes. If there aren't any, then it knows this is a copy. This next method is quite a common one. The 3 steps you see overall average out to the same amount of time, so this isn't a long track protection scheme. However, these steps are usually spread over 3 sectors, and the software will measure the time taken to read each individual sector. The first sector would read a little faster, the second at normal speed, and the third a little slower. If you copy the disk, then these will flatten back out again, and all the timings will read the same. The software would measure the timings of these 3 sectors, and if the speed of these varied within a certain percentage, then it knew this was the original disk. Finally, I want to talk about perhaps my favourite, weak bits, or flaky bits as they're also known. They're much talked about, but I don't think anyone's actually physically seen them. Imagine rereading a track several times, and intermittently 1 or 2 bits seem to flip positions. This can't be achieved using unformatted data, as we're literally talking about 1 or 2 bits being flipped, and these occur during normal flux transitions at around 4 to 6 microseconds. This was used by several games, and this pattern you can see here was actually taken from Dungeon Master. This copy protection method worked by encoding some special data into one of the sectors. On track 0, upper side, see the strange sector to the left. Zooming in doesn't reveal much, but HXC doesn't like it. That is until we switch to stream mode. There's an interesting pattern going on here. This pattern is deliberately designed to confuse the PLL and produce edge cases where flux transitions can occur on a clock boundary. What really surprised me is, it actually worked on my simulator. It all looks okay, but if you look closely at the graphs at the bottom, see how every now and then there's a twitch in the graphs? That's your weak bit. I find this almost mesmerising to watch. I don't think I expected to be able to see this happen. This isn't faked, this is genuinely happening on its own. Now once again, obviously copying a disk like this would take a snapshot, which means the data wouldn't change. I'm going to leave this here for a few moments for you to watch. The reason I wrote the simulator was I was updating Floppy Bridge, the plugin that allows you to use real floppy disks in real time in WinUAE, and I wanted to test some new code. I honestly did a double take when I saw the weak bits twitching the way they do. I just didn't expect it. Some really clever people spent a lot of time creating these clever schemes. It's unfortunate that in the end most of these were simply cracked by bypassing the checks themselves. I hope you found that video interesting. If you did, then give the video a thumbs up and think about subscribing to my channel. Also, if you're enjoying my videos, then why not support me on Patreon? Thanks for watching, and I'll see you next time.